Professor Blitzstein is a professor of the practice of statistics. He is known for teaching the popular class, Stat 110, Introduction to Probability, which holds over 300 students each fall. He also has over 200,000 subscribers to the class on iTunes U. His research interests focus on statistical inference for complex networks. Professor Blitzstein also enjoys chess and advises the Harvard Chess Club. Please join us in welcoming Professor Blitzstein.
Thank you all for coming. Thanks for the introduction. Let's get started right away. The title of my talk is The Soul of Statistics. Let's start with a motivating example before I tell you what I think the soul of statistics is. So Abraham Wald was a famous statistician, and during World War II, too many British bombers were being shot down by the Nazis, so he was consulting with them about trying to figure out where to put more armor. You know, they want to put more armor, but the armor is heavy and expensive. They can't just put armor everywhere, so where do you put the armor? Okay, so I drew some airplanes here. These don't really look like the bombers, but that's okay. So here's some airplanes, and I just drew some bullet holes. There's one. Sorry, I didn't have a warning that there'd be graphic violence here, so hopefully no one is too squeamish. There's another one, another one, another one. Bam, 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 bam. So these are I just made up some bullet holes on these planes, and these are the planes that they get to observe. Okay. Just as an example, and so they brought in Wald to ask, you know, where should they be putting more armor? Well, the obvious thing to do is you know, look at where all the planes are sustaining heavy damage and armor those regions more. However, Wald said to do the exact opposite. Look for the parts of the planes where there's very little or no damage on the planes that came back. The reason is, so for this example, I protected the nose on all of these planes. And so what's really going on here? Well, what we're really interested in is the planes that we didn't see. Those are the planes that didn't come back. The ones that you actually get to see are the planes that actually survived well enough to return. So there's some statistical thinking in there. How do you learn about the planes you don't get to see? And you know that requires some statistical assumptions and statistical thinking about what do you do about the missing data, right? So maybe what if it looks like this? This plane, we didn't get to see it because that's like the Achilles heel or the Achilles nose of the plane, and maybe there's like a whole army of these like Rudolph the red-nosed aircraft that we don't get to see any of them because they all died and we only saw the other ones. So that's where you put the armor. So that was the idea. It's a pretty simple idea in retrospect, but easy to miss if you're not thinking statistically. Okay, so that's an example of what's called selection bias in statistics. What we know about is what we get to see, which is where the bullet holes are distributed for the planes that actually return. But that's not what we're interested in. We want to know about the planes that didn't make it back. Okay, so how do we link those two things? That's a statistical problem. Now we're ready to say, what's the soul of statistics? I won't keep you in suspense. Conditioning is the soul of statistics. That means conditional probability, for those of you who know what that is. If you don't know what conditional probability, all it means is that we're given information. We always have information wherever we're doing. It's all conditional on the information we have. And conditional probability tells us how to update our beliefs based on information that we're able to observe. Every probability is conditional. And so that's the point of view here. Whenever you have a data set, you want to think about how it was sampled. So this is just a picture that I'm not really going to talk about of a network, which is something I work on, where there's a huge amount of interest in networks these days, but a lot of that work ignores where did the network come from, how is it sampled, and that can lead to very misleading answers if you ignore the sampling, if you're not careful about what you're conditioning on. And, you know, this is supposed to be Harvard Thinks Big, so I'm going to try to think really big. That this is not just the soul of statistics. This is everything, because we wouldn't be, if what I said was not true, we wouldn't be here having this conversation. It's all conditional on a huge conditional probability calculation that we can't actually do of things that brought us to this room to have this conversation right now. Everything is conditional. Okay, so here's another example. This is a longevity study from 1835. Lombard was interested in collecting huge amounts of data, a very impressive data collection effort for how long people in different professions lived. Okay, so I'll just give you a few. I chose a few examples. That's a selection bias too. It's the ones that I felt like choosing because it's a short talk. So here's the profession. Here's the average longevity in his data set. So it turned out that the first or second longest living people in his data set were chocolate makers. So I was very happy to see that because I really like chocolate. They lived to be 73.6, which lifespans have improved from 1835 to now, so that's actually quite good back then. And this is not second on the list, but one that I was interested in was professors lived to be 66.6. So it's a little bit sad. I could have, if I had chosen a different career path, I could have lived 7 years longer and had all the chocolate that I want. There is a sample size issue here, which is he only had 9 chocolate makers in his sample. That's a very small sample. There are a lot more professors than chocolate makers in his study. But anyway, let's go on. Clocksmiths lived to be 55.3, so that's less attractive. Locksmiths, 47.2. I was trying to figure out why is there this discrepancy between clocksmiths and locksmiths? So what could explain this? I don't have an answer yet. One more that is of interest to all of us is students. Unfortunately, I have some bad news for all the students here. In his study, he found the average longevity of students was 20.2 years. So I didn't want to be like, get this event off to a depressing start. I'm the first speaker, and I don't want everyone to be too depressed to pay attention to the other talks that are coming up. 20.2 years, it's worrisome. I recommend that if you haven't seen Steve Jobs' commencement address from Stanford, 2005, I was there because I was at Stanford. It's a great talk. Thanks. About living each day to the max and all that. Okay, but there's an obvious problem with that logic, right? Which is, what are you conditioning on? A student, 20 years old is a normal age for a student. Okay, so it's kind of obvious to see what goes wrong. It's a good example of looking at an extreme case, because in the earlier professions, it's not obvious that there are all kinds of biases going on. But when you see the simple and extreme case of a student, you can see that the whole thing is very suspicious. There's another issue. I want to mention one more thing about that. About censoring, which is that we only know how long people lived after they died, okay? So usually it's a lot harder to talk to dead people than to talk to live people, and Professor Dench will be telling us about talking to dead people in detail. But this is one case where it's much easier to deal with the dead people because we know how long they lived, okay? So there's a large amount of statistical survival analysis is a field to try to deal with the fact that we don't know how long the living people are going to continue to live, and if we're not careful about that, we're going to get some bad bias. All right, one more example, which is a very famous one in statistics, is regression towards the mean, and it's everywhere. So just to take an example, if you're not familiar with this, take test scores. So you have a group of students who take the SAT. And then suppose that the ones who did really well take it again, and the ones who did really poorly take it again. So we're doing a selection, okay? Well, regression towards the mean says that we expect that the students who did really well on the SAT, when they retake it, their scores are going to tend to go down towards the mean. The ones who did really poorly are going to go up. There's examples everywhere. One of the first examples, I'm not going to go through this data table here, but that's just for historical curiosity. Sir Francis Galton, who was a cousin of Darwin, was one of the first, or possibly the first person to clearly explain regression towards the mean. And he discovered it by studying heights, parents' and children's heights. And he found that, for example, if you look at fathers and sons, so we don't have to worry about differences gender differences in heights. Let's just take fathers and sons. Okay, so he looked at very tall fathers. How tall are their sons? Well, the sons are still pretty tall, but they were regressing towards the mean. Okay, and very short fathers, their sons tend to be taller, not all the way to the mean. This is regression toward the mean, not to the mean, but it's moving in that direction. That phenomenon is everywhere in statistics and in life, so if you have your eyes open to look for it, that's a good thing. And so I just want to quickly quote Daniel Kahneman, because it's a beautiful quote about regression towards the mean. He said, "I had the most satisfying eureka experience of my career while attempting to teach flight instructors that praise is more effective than punishment for promoting skill learning." And when he gave that talk, a flight instructor objected, "On many occasions I've praised flight cadets for clean execution of some aerobatic maneuver, and in general, when they try it again, they do worse. On the other hand, I've often screamed at cadets for bad execution, and then they do better the next time. So don't tell me that reinforcement works and punishment does not." And Kahneman said that's a joyous moment because what he realized is we tend to reward others when they do well and punish them when they do badly. And because there's regression to the mean, he should say toward the mean, it is part of the human condition that we are statistically punished for rewarding others and rewarded for punishing them. And so there are a lot of misconceptions about regression toward the mean that I don't have time to get into detail of, but I wanted to do a quick little picture illustrating a hypothetical thought experiment. What would the world be like without regression toward the mean? Because a lot of people seem to have the misconception that regression toward the mean would mean that everyone is going to be, eventually converging to the same value. And actually, without regression toward the mean, we need regression toward the mean in order to have stability in the population. So I just made up a simple example where suppose we had 3 people, 3 different heights, and suppose each person has a child who's equally likely to be a little bit shorter, the same height, or a little bit taller. Okay, so I just gave them three kids each. A little shorter, same height, a little bit taller. So that's the next generation. Then I just took that generation and just rearranged it. These are the same people. Now, same thing happens again. That's the next generation. And then I'll just take one more generation. This is what the population would look like without regression toward the mean. What you see is after only 3 or 4 generations, you're going to see giant, 10-foot people walking around, and you have little 4-inch people, things like that. That's what the world would be like without regression toward the mean. Okay, lastly, I want to tie this back to just kind of personal perspective on teaching and research, which is something I call the conditional golden rule. So this was a course evaluation I got in the Q Guide a few years ago. So someone wrote, it was a class, this is about Stat 110, it was a class that was designed by Blitz with the credo, I wanted to teach a class that I would want to take myself. So I was really happy when I saw that, because it was a nice comment, but it also reminded me of something that I had forgotten that I had said, and I kind of liked that. However, in the interest of full disclosure, that same year there was also a comment that said, writes horrible problem sets that only cause pain, not learning. So unfortunately, I try to be logical. The logical conclusion from these 2 things is that I'm a masochist. So let me just... So let me just tell you what the conditional golden rule is, and then I'll stop. This is my philosophy of teaching in a nutshell. Do unto others as you would have do unto you, except it's conditional, right? Everything is conditional. It's the class that I would take conditionally on having the same interests and background and knowledge. So I just try to do the conditional golden rule. I'm trying to follow it right now in giving this talk. And if I failed, blame the conditional golden rule. Or blame the fact that conditional probability is hard, as we see in Stat 110. It's hard, but it's worth thinking about. Okay, so I just want to thank the organizers and thank my colleagues, especially Carl Morris, Xiaoli Meng, and Dave Harrington, and all my Stat 110 students and TFs, and all of you for coming. Thank you.